So what you see here is, so is another model, right? So in the earlier case, what you receive in the receiver section y, which is continuous, which is ranging from minus infinity to plus infinity. But now what you see here is the model. We have an intermediate variable y1, right? After doing this additive Gaussian noise, right? And after applying the threshold, we can assume that we are getting it as what? Y equal to 1 or 0, right? So if you make this as a black box, these two combined together as a black box, this is a box now, right? So what, so as far as this is considered, what is being transmitted from the transmitter x, right? So that takes that value 1 or 0. I mean, it is the identity, right? So the actual amplitude could be 1 and minus 1, right? This is just the identity what I'm telling. So what you are having here x is taking that value 1 or 0 in the transmitter section, right? Now in the receiver section, what you get is y equal to 1 and y equal to 0. But still you can actually do this better detection, right? Improvement can be done. So that is what we discussed in the previous channel. This black box is actually modeled using the channel characteristics like this, right? So this is what we discussed. This is what we are having. This is x here and this is y here, right? So this is 0 and 1 and this is again 0 and 1 here, and you have the probability of getting 0 when 0 is transmitted. Let us say this is alpha and this is beta here. Probability of getting 1 when 0 is transmitted, this is going to be 1 minus alpha and this is going to be over 1 minus beta, right? So this is the characteristics of this channel, what is given in this black box, this green color, right? So this is what is given to you. And then we discussed about the Bayes technique. We discussed about this Bayes technique, how to design this detection block, right? So that is what we discussed, right? So in that case we had 4 cases, case 1, case 2 and all, we know that, right? Case 1, case 2, case 3 and then case 4, because in this case the possible values of y's are only 2, right? Either 1 or 0. So we are going to discuss about this continuous version of this problem in the coming class, but so just to recollect, because we had a gap, right? So I just wanted to recollect whatever we discussed. So it is like, so we had something like gamma 1 is 1, gamma naught equal to what? 0, and then we had gamma 1 equal to 0, and then gamma naught equal to 1, and we had this gamma 1 2 is equal to, right, 1 and 0 here, and then gamma naught that is equal to this null here, and finally we have this gamma 1 is null and gamma naught is 1 and 0, right? So we had this possible, right, cases, right? But the ultimate objective function to choose one among these case, right? So you know the rule what it is, right? Case 1 is one rule, case 2 is the second rule, and then third rule and fourth rule, we know that, right? So what does it mean? So if for example, if I take this case 1, so what is that meaning of that? How will you understand that meaning of this case 1? That is a rule now. So how to interpret that? I'm talking about this detection block. So whatever we had here, this detection block, that alone here it is written, right? So this detection block has this input as y only. So if I consider this case 1, what does it mean? When you are getting this y equal to 1, you have to decide that what is being transmitted originally from the transmitter here is x equal to 1. When y is equal to 0, you are deciding that x equal to 0. So that is the meaning of this case 1, right? So in case of case 2, for example, this case 2 here, in this case it is going to be that other way around, right? So when you get y equal to 1, you decide that it is x equal to 0. when y equal to 0 is what you receive, you have to decide that x equal to 1. So it is the other way around. That is the case 2 here. And then when you go for this 3, right? So in that case, you have to go for what? So in both the case, right? So when you have this, when you have y equal to 1 or y equal to 0, in both the case, you are going to decide that x is equal to 1. So that is the third rule. And finally, that fourth rule, what you get here is either it's going to be y equal to 0 or y equal to 1. You are going to decide this fourth rule as x equal to 0, right? So these are all the rules, right? So now which rule I have to freeze? Which rule I have to freeze? And what are the things it depends on, right? So that is what this, we had what is called this Bayes. We had a Bayes rule, right? So what is that Bayes? We have to create the cost involved in doing this mistake. This is the average cost involved in doing this error, right? So it is like, you know, so when 0 is transmitted, if this y lies in the region gamma 1, so there is error. This is the error in it, right? So similarly, when 1 is transmitted and you are received y, where values for this y, if it lies in gamma naught, there is another error, right? So these two are the error, right? So it also depends upon this prior probability. Pi naught is the prior probability, and here we have, right, we have this prior probability pi 1 also. What is prior probability? As you know, prior probability is nothing but, it is a notation what I'm using it as a pi naught, don't get confused. It is nothing but probability of x equal to 0, and pi 1 is, that is equal to what? Probability of x equal to. So this is what we say that it is a Bayes rule, right? So we have to choose this gamma naught and gamma 1. In other words, you have to find, you have to optimize the set. You have to do this partition set gamma naught and gamma 1 such that this cost function is actually getting minimized. The average cost C bar is getting minimized. How to get this gamma 1 and gamma naught is the question, right? So that is what we discussed, right? And most important to understand here is this, the prior probability. It also depends upon the prior probability. That is very important. So if I want to have a proper design for the detection block, I must know what could be the prior probability. I mean, the prior probability means the probability of x equal to 0 being transmitted from the transmitter, right? So this one, what is this probability, right? So this probability must be known to you. This must be known to you. Okay, this must be known to you. So that is the drawback of this Bayes. Bayes is the best. Bayes is the best way, right? Best way to, for the detection, for designing or for detection theory, detection block, for designing the detection block, for getting, right, for getting this detection block. But it depends on the prior probability. So what is the deal? The problem is the prior probability is not known. If it deviates, if the data what is being transmitted which is not in our control, right? Suppose that if it get deviates, then what will happen? Then we cannot say that this cost function is going to be that minimum in that case, right? So that is the reason we are actually moving towards the next technique, what is called the minimax technique. I'm just discussing these things because you must know the reason why this minimax technique is important. Minimax technique, we are going for this minimax technique because, right, in real time, if this pi naught deviates, if it deviates, then your Bayes, you know, is not the best. base is not the best, right? When pi naught deviates, that is important. Base is the best if I know what is the value of pi naught, right? If pi naught deviates, then base is not the proper solution. So then what we have to do is we have to go for something like, the worst case scenario, right? So what is that? We have to look for this worst case, and then out of that, we have to go for the best. So we'll see what is that minimax technique, right? So minimax technique doesn't have the information regarding this prior probability. That is the first one, right? So to understand that, you need to actually plot the cost function, right, as a function of this prior probability, right? Before that, I would like to tell few things. Suppose that your rule is fixed. Let us say, let me put it as like this: C bar. Once this gamma 1, this is very important, listen carefully. Once this gamma 1 and gamma naught are freezed, it means that your rule is ready. Your rule is ready for a particular prior probability. You have freeze this rule, right? We don't know what actually the prior probability is, but you freeze this gamma naught and gamma naught, gamma 1 and gamma naught, assuming some prior probability, pi naught, right? So it is not the original one, right? So this is that assumed, you can say that assumed prior probability. It is not, because we don't know the prior probability, so we call this as assumed prior probability. I mean, some estimation of the prior probability. With that, we are designing this base, and you got this gamma 1 and gamma naught. Once this gamma naught and gamma 1 is freezed, then this probability is fixed actually. P naught of gamma 1 and P1 of gamma naught. These two are fixed actually. These two values are fixed, right? Now I'm rewriting this expression now, because the prior probability is not actually pi naught, right? It is assumed prior probability. Now it is getting deviated. Once it is getting deviated, let me put in real time, this prior probability is not pi naught. Let us say that it is P, right? P into, this is some constant. Let us put this constant as K1 plus pi 1. I mean, it is nothing but 1 minus P, right? This prior probability. Remember that it is a deviated one. It is a deviated. I mean, it is not the original pi naught, right? So this is the assumed prior probability, and you have designed it. I'm not saying this is the true value, right? So you have assumed some prior probability and you have designed it. Once you design that, your P naught of gamma 1 and P1 of gamma naught, that is freezed. So in that case, they are constant. So we call it as K1 and K2, right? Now your prior probability is getting deviated. It means that in place of pi naught, I am replacing with this P, right? So as P changes, your cost function is going to change. And it is seen as a linear equation. You see that this is a linear equation actually. It's a straight line. What I'm trying to say here is, once your gamma naught and gamma 1 are freezed, your base cost, right, C bar, changes with what? The prior probability, right? That is actually getting deviated from the original value. So are you getting this? This is very important. What I'm trying to say here is, the base cost varies linearly with what? Deviating prior probability. Is that fine? Okay. Are you getting this? Right? So I hope you got it. Right? Now you can see the graph. You will get a better understanding of what I am trying to say. Are you able to hear? Are you listening? Yeah. Okay, right. So now you can see to this graph. this is the important graph to understand this minimax technique. This is the important graph what you see here, right? So what is that valid cost function curve, right? So I have drawn just like that, one as a concave, the another one is the convex, right? And as you know, once it is designed, once this gamma and gamma 1, once this gamma naught and gamma 1 is freezed, right, your base cost, right, is actually going to vary linearly with the prior probability. So this is that prior probability. What you see in this graph is the x-axis is the prior probability, deviating prior probability, we can say, right? And you can say, you know, P1, right? So this, I mean, it need not be there. Base rule. Once this base rule is obtained, this is the cost function you are getting. I write it here again. The average cost function is going to be your pi naught into p naught of gamma 1, right, plus 1 minus pi naught into p1 of gamma naught, right? Sorry. Yeah, I repeat, this graph, what you see here, this curve is the base cost. This is the base cost curve. And how it should look, that is, for that only I have given this 4 figure here, subplots, right? But as of now, you concentrate only on this A. Only on A, don't see B or C or D, then you will get confused, right? You see only this A, right? So this is the base cost. This is the base cost for every prior probability, right? So you know that for every prior probability, right, you get, so I'll put it here like to make you understand how this graph is plotted. Let me put like this. For every prior probability, some value of pi naught, right, prior probability, you actually get the partition, right? Gamma naught and gamma 1 you will get, right? So once you get this gamma naught and gamma 1, then your p naught of gamma 1 and p1 of gamma naught are fixed. Okay, that is fine. But once this gamma naught and gamma 1 is obtained for one particular prior probability, as you know, for which prior probability it is done, you know what is the value of this base cost. C bar, using this expression, we can actually calculate. So if I do so for every prior probability, I think we have seen this one for the binary case. For the binary case, how it looked like, we know that for the binary case, it looked like this, right? So we had this positive slope, and then we had some negative slope, and further one more slope. 3 straight lines we got it in case of binary, right? So this figure is more general. This figure is for more general case, right? So I'm not saying that, you know, this is the base cost should look like this. You know, we have another way here written this base cost. The curve what you see here is the base cost for various values of the prior probability. It is like that, right? So what I'm trying to say here is, if it is the assumed prior probability, and then this is the base cost, right? So if I keep on changing this prior probability, we will get what? Different base cost here. You see that? So these are all the different base cost what you get. So these are all the different base cost what you get for different values of this, right? Now this straight line is basically, you have actually designed the base reductor for the assumed prior probability of P1. But now in that case, what is happening? These two are freezed. P naught of gamma 1 and P1 of gamma naught is freezed. Then your pi naught is getting changed. It means that it is getting deviated from this value. When it is getting deviated from this value, your base cost, right, it is actually changing now as a linear. That is what it is given as a linear graph. So this straight line, right, is the base cost, right, after freezing gamma naught and gamma 1 with pi naught as p1. So that is the meaning of it. So it is slightly difficult to interpret. I will repeat again. So what I'm trying to say here is you are actually designing this base for some pi naught. Let us say that is p1. You are designing that it is a p1, right? But now it is getting deviated from this p1, right? So your original prior probability is not p1 now. In reality, it is getting deviated. When it is getting deviated, right, your base cost is actually changing as a function of the prior probability, which is going to be the state line. That is what this state line is actually coming into picture, right? So this is like, what I have drawn. This one is for the 4 different instances, assuming that this is the base cost for every prior probability, right? This is the base cost for designed for every prior probability. This is again this base cost, and this is again this base cost for every prior probability, right? So among these 4, right, so you have to see whichever is the valid curve, right? We'll see that one by one. Is that a valid one or not? That we need to freeze. That is one thing, right? See, for example, if you consider this A, is that a valid curve to say that it is a base cost? For example, you consider this P2 is the prior probability. As this base here, you are getting, right? But there exists some other partitioning. There exists some other partitioning, one which is giving you the base cost. I mean, which is giving you the cost which is lesser than this base cost. Whatever is there in that curve is the base cost. Okay, this is that base cost, and whatever you see in the state line, this point is right. So this is what actually you are able to get because you already designed the base for this P1 and your prior probability is getting changed to P2. In that case, that cost what you get is here. But if the prior probability is P2, as far as this original method, what actually you get this base cost is this. You see that the base cost is greater than what actually is marked at the bottom, which is not correct, right? So the base cost is the one which is supposed to be the least. Base cost is the least cost, right? It is the least cost what you can achieve for one particular prior probability. So this graph is actually invalid. So you will not get the curve like this for the base cost, right? Like this. And similarly, the state line, state line need not be in this form, right? It need not be in the tangent to this curve like what I have drawn. It could be something like this also. So first of all, we concluded that it is not going to be in this shape. So it is necessary to be the other way around, right? It is. So this is that a valid now? We'll check now. This is not valid, right? Valid in the sense I am giving only the example, right? So how the base cost is changing, right? So if I have this base cost changing like this, right? So now there exists one more rule available that gives you the cost lesser than the base cost, which is not allowed, right? Base cost needs to be the least, but there exists another cost here which is lesser than this, right? That means that it is not the valid curve, right? I mean, this is not this could not be the base cost curve. So another case, now the case 2 here, we have the curve now in the other way around because this way which is not perfect now. So you are considering this other way around. So now you are considering again the same point P1 where you are actually finding out this base cost at this point here, right? And as usual, when it is getting deviated, you are drawing the state line. So this is the deviated cost here. So it is like that. So the same way, so if I consider this intermediate region here, somewhere in the middle, your base cost happen to be greater. You see that there exists another rule, right? which is lesser than this base cost. So this is also not valid. This is also not valid here, right? So the straight line should be the tangent. It should be like this one. So we'll see this third one. Third one is actually fine. Third and fourth, right? So that is fine actually. This and this, these two are fine. So in fact, we already, with the values, we already shown that how the graph is there for the binary case. Binary case also, it was like this, we got the shape like this, right? So it is also something similar to this, but here it is piecewise linear, but here in this case, it is a continuous, right? So in case, so this is looking like what we expected, right? So now let me once again discuss about this minimax, right? So now here Q1 is the assumed prior probability, and you have the base cost for every prior probability, right? So you know what it means. What I really mean by that is, for one particular prior probability, you are actually designing. Designing means getting this gamma naught and gamma 1 and finding out what is that average cost. And like that, you are actually plotting, and this is the base cost curve, right? So these are all the base cost curve. But now let us assume the practical case scenario. The prior probability is Q1, and you have obtained this base cost to be like this. Now it is getting deviated. Your original prior probability is not this, right? It is getting deviated. As you know, as this prior probability is getting deviated, right, your cost function is actually changing with linear, right? This is a straight line which is actually changing with in a linear fashion like this. It is actually acting like a tangent, and this is a valid curve because the base cost is actually below than this tangent. All the cost, the base cost should be, because for any arbitrary prior probability, the best choice, if I choose some arbitrary prior probability, the best choice should be the base solution only. So that is true here. This is actually getting with some other rule, but this is the rule with base. Base rule is always giving you the least cost for any arbitrary prior probability. So it is the valid curve. Similarly, this is also the valid curve, right? So here it is chosen, it is Q2 as a assumed prior probability, and how that is changing, how the cost function is changing if this prior probability is getting deviated from the assumed prior probability. That is what the thing, right? So now you can see to this the C and D graph to make you understand better, right? So that one I would like to repeat. this third and C and D, this is anyhow is not a proper curve. This is just to make you understand that the base cost function as a function of this prior probability will not look like this, in both the case whatever I have done, right? So, and these two are the valid one. C and D, they are the valid one. It should look like this only, right? So now what this figure is actually giving you, you are actually fixing the prior probability, and you are designing this base. Designing the base means what? You are actually getting this gamma naught and gamma 1. That is the meaning of, right? And now once this gamma naught and gamma 1 is freezed, then the cost function, right, P naught of gamma 1 plus 1 minus pi naught P1 of gamma naught, and this value is exactly this. This value is exactly this, right? And your pi naught value is assumed as what? Q1 in this. This is what is Q1. Fine. This is done here, right? So pi naught is Q1, and you have this P naught of gamma 1 and P1 of gamma naught, and that is giving you some cost function, and that value is exactly this. Fine. Now what I'm telling here is, you have already now freezed this partition. Rule is fixed. That is, your gamma naught and gamma 1 is fixed. Rule is fixed. Now I'm rewriting this function, right, in a more general way, right, without putting this pi naught as Q1. Instead, I'm putting it as P. It's a variable. So this is constant now. That is constant now, K1. And the second part, 1 minus P, right? And this is another constant, K2. And this is the straight line as a function of P. That is what I'm telling, right? So this is the base cost. Now you are writing the expression just by replacing this phi naught with what? P as a variable, right? At P equal to Q1, you get actually base. This is C bar, base you get, right? But now this is a more general thing, right? So that is the straight line what you are seeing here, which is actually the function of P, which is the function of P here, right? That is the straight line here. Why I am telling this one, right? So because we don't know the prior probability, that is the issue. Issue is I don't know what is this, what is the prior probability. If I know prior probability, there is nothing to discuss. It's very simple. You have to get this gamma naught and gamma 1 such that this is getting minimized. Job over. But now pi naught is not known. Then where should I keep this pi naught out, or where should I design, the Bayes, right? By what is the choice I have to choose for this prior probability, which gives the Bayes, right? So in other words, what is the value of pi naught I have to fix? What to fix? That is the question. What to fix? Right? I can fix here, I can fix here, I can fix here, anywhere, right? So I can fix anywhere in this. So what is this you are getting here? So this is basically the error or the cost value, conditional cost we can say, right? It is nothing but P naught of gamma 1 and P1 of gamma naught. That is what it is actually giving you, right? This conditional cost, right? When 0 is transmitted and then when 1 is transmitted, what is the cost involved? Right? In other words, in this expression, if I put P equal to 0, in this expression, if you put P equal to 0, you get what? You get K1, right? You get K1. In this expression, when P equal to 0, you get K1, right? So this is what I'm telling, that it is K1 here. And when you put P equal to 1, right? I'm sorry, it is K2. I'm sorry. It should be the other way around. When P equal to 0, it should be K2 here, right? When P equal to 1, you get K1 here, right? So when P equal to 0, you are getting K2, right? And when P equal to 1, you are getting it as what? K1 here. So this is the straight line what you are getting, right? So what is K1 and K2? In this expression, we know that K1 is nothing but P naught of gamma 1 and your K2 is P1 of gamma naught. It's like that, right? So this is K1 and this is K2 here. When P equal to 0, right? So this becomes 0 and then you get K2. And when P equal to 1, this becomes 0 and this becomes K1, right? So this is what you are getting, right? So this straight line. So we are trying to minimize this conditional cost. So if I choose Q1 here, this conditional cost is greater than this conditional cost. When we choose this Q2 here, I mean another prior probability, right? If I freeze this as a point, in this case, B naught of Q2 is lesser than what? B1 of Q2, right? So now the question is, what could be the better choice for which this conditional costs are, right? If I try to minimize one conditional cost, the another conditional cost is actually getting increased. That is what is happening, right? If I try to minimize this K2, your K1 will get increased. This is the consequence. If I try to decrease this K1, K2 will increase, right? So this is the case, right? So if K2 is, right, if I try to decrease this K2, K1 will increase. If I try to decrease this K1, K2 will increase. That is the consequence. What is that you are getting, right? So what could be the better choice for which this K1 and K2 no is identical. What is the choice for this prior probability? Somebody tell me the answer. Hello. Excellent. I think some of you are answering properly, right? So it is the point where the slope is 0, for which it is going to be that maxima point here, somewhere this point here, right? So where actually you get, right, your K2 and K1, right? So both are going to be the same, right? So it also, even if it is getting deviated, see, you are designing this one with this as a value, right? Let us say this is Q. You are designing this base with Q, and you can see that even in real time, if it is getting deviated, the cost function is not actually changing. You see that it is not changing, it is fixed. It is fixed to be equal to K1 equal to K2, and that is going to be constant. That is equal to constant. Even if you change your, if it gets changed, right? The prior probability, if it gets changed, even then the cost function is not actually changing, which is the same value as that of what you actually designed. So I'm not saying this is the best. I'm not saying this is the best, right? You have to be careful. Base is always the best. Base is the best, right? But for getting this base, you need this prior probability. So when this prior probability is not known, you are going to fix some prior probability here, which is Q, for which your cost function is not getting deviated, even if it is getting deviated in the, even if the prior probability is getting deviated in the real time, which is this point. So to answer the final statement, right? So the final statement, what I want to say here is, in case of minimax technique, we can say that minimax technique is same, it's nothing, right? It is same as of the Bayes technique. There is no difference in it. It's the same as that of this Bayes technique, but you have to fix the prior probability phi naught as Q, for which you are getting that maximum value of this base cost when this prior probability is changing all the way from where 0 to 1. Or if I am calling this as a function CB of P, you have to choose phi naught to be Q for max of what? Max of CB of P. That is the better way to, right? So instead of pi naught, I will put it as P, because here given P in the figure, right? So it is like that. I repeat, base cost. Once again, we will discuss this one in detail in the next class to make you understand. Now you have to understand that base cost is same as that of the, sorry, minimax technique is same as that of the Bayes technique, designed for this prior probability P equal to Q, for which CB of P is maximum, right? So that is what this minimax technique, right? Any questions? We'll stop here, we'll continue in the next class. we shall discuss this flip task details and then tomorrow. Tomorrow we will discuss because it's already time, right? We shall discuss those things tomorrow. We'll stop here, right? So once again, we will discuss about this minimax technique tomorrow so that you will get it more clear. Now, today you actually got introduced this minimax technique, right? So tomorrow you get a better clarity on that. Okay.